Welcome to Tollefson Physics. So what we're going to work on today is we're going to look at how energy can be stored in one form and transferred to another location. And so we're going to create what are known as energy bar charts. Sometimes they're called LOL diagrams, and I'll show you why that is in a moment. So let's think about a situation. So I have this situation here where I have a person standing on top of a building and they're going to drop a ball. All right, and so we're gonna look at where is the energy stored in the ball Earth system. So that's something that we're going to define. So why is this sometimes called an LOL diagram? Well, here's my starting bar chart, and here's my ending bar chart, and there's my system. All right, so this is initial, this is final. Right? So I'm going to look, when I analyze energy, I'm going to look at what's happening in one spot, compare it to another spot. And so to do that, I'm going to have to define what I'm looking at. All right? So I don't actually care about the person in this case. All I care about is the ball. But the ball is in the Earth's gravitational field, so I'm going to include that. So this circle here indicates what I'm thinking about for my system. All right, so now we're going to consider where is the energy stored. And now in physics, we're going to deal mostly with what's called mechanical energy. And so when we're dealing with mechanical energy, we're going to be looking at just a couple things. We're going to ask ourselves a couple questions. So first off, K stands for kinetic energy. And kinetic energy is the energy of motion. Is it moving, right? Is it moving? All right, so that's kinetic energy, capital K. So gravitational potential energy is what UG stands for. So U means potential energy. The G means gravitational potential energy. All right, and so that's why the Earth is involved. It depends on where you put something, right? The higher you put something up, the more distance it could potentially fall. And so that's an important thing to consider. And then we have US, which is spring or elastic potential energy, and I'll just abbreviate that PE. So basically with gravitational potential energy, is it up high? Or has it the ability to change height? And this is it involves something that stretches. Okay? So now let's look at our ball Earth system. So now starting up here, so this is my initial location. Where is the energy stored? So first thing I'm going to ask myself, is it moving? Okay, well, I'm just holding onto the ball, so the answer is no. It's not moving, so there's no kinetic energy. Is it up high? Well, yeah, in this particular case it is. So I'm just going to make a bar, and I'm going to just make arbitrary boxes. So I'm going to make it 4 boxes high. I don't know how much energy it has because I have no numbers here, but let's just say it's 4 boxes high. All right, and then does this involve something stretchy? In this case, no. So it looks like when I'm holding a ball up high, my initial energy is all stored in the ball in the gravitational field of the Earth. So then when I let go of the ball, we all know what's going to happen. It's going to speed up as it falls down. So I'm going to look at what is this final location right before it hits the ground. Okay? So is it moving right before it hits the ground? Oh yeah, it's definitely moving. Is it up high? Well, no, it's about to hit the ground, so I'm going to consider that it's basically at ground level. So, no, there is no gravitational potential energy. As we said before, there's no elastic potential energy, so there's no spring or anything associated with that. And then there's one more thing that's listed over here. It says EDIS, which is dissipated energy. So this is like due to things like friction. So it's something that is difficult to get back. So if we have friction, then it's really hard to get that energy back. It goes into heating up the surfaces maybe making some sound, things like that. Matter of fact, something like that will happen when the ball hits the ground too. The ground will absorb some energy. So, but we're not looking at that. We're looking right before it hits the ground. So that's what that last one is, dissipated energy. So the idea though is energy is conserved. So if all of my energy falls within this system, then if I have 4 bars of energy to start with, well then I must have 4 bars of energy to end with. All right, and so that's this big idea, conservation of energy, that will be coming back to time and time again. So now, why is the system important? Well, let's do the same example, but let's not include the Earth as part of the system. Oh, what do you mean, not include the Earth? All right, so now I'm going to look at just the ball, and I have my different types of energy that I can consider. So when I'm standing on top of the building, is it moving? It's still not moving. Is there elastic potential energy? No, there's nothing stretchy. Well, is there gravitational potential energy? Not if I don't include the Earth, right? So I need the Earth to be part of that. So if I don't consider the Earth, if I'm just looking at the ball, that's it. And I'm allowed to do this, by the way. I'm just looking at the ball. Then I actually have what appears to be no initial energy, right? So this is my initial energy, which I'll indicate as E naught. That's a small zero. I didn't do a good job. All right. And then, well, what about at the end of the day, right? Kinetic, gravitational, spring, dissipated, right? So is it moving? Yeah, it's moving. Oh, let's use a different color. So yeah, it's moving, just like before. The ball is moving. We can definitely say that. I'll make it 4 high. Okay, we aren't considering the Earth, so we really can't use gravitational potential energy. No spring, no dissipated energy. So this is my final energy. Now, wait, right? So it looks like I have energy that formed. Right? What's this conservation of energy idea? Well, in this system, it appears, if I just look at the ball, that it's magically speeding up. But we know why it's speeding up. It's a gravitational field of the Earth. So there's another way to look at this. So the energy is coming from the Earth. The Earth is outside my system now, right? It's not part of the system. So what it's doing is it's putting energy into the ball. So 1, 2, 3, 4 boxes of energy. So whenever we put energy into or take it out of a system, it's called work. So I'm going to call that W. This is known as work. So work actually can allow us to change the energy of a system. And that's what we see here. So what I'm trying to show you here is there's 2 ways that I can look at the exact same system. If I include the Earth, I can talk about gravitational potential energy being transferred to kinetic energy. But I also could just look at just the ball and see that the Earth does work on the ball, which means I'm going to add energy to the system, to cause that ball to speed up and give me kinetic energy. All right, so these energy bar diagrams are going to be really important for us to be able to identify what's happening before and after any situation that we're interested in, and then we can potentially calculate interesting things about what that energy is telling us. It might be the height of an object, it might be the velocity of an object. Heck, it might actually help us design a roller coaster. All right, so hopefully that helped you out, and we'll see you next time. The only way to learn physics is by doing physics. So now you tried this problem. So imagine that a ball is being thrown up straight in the air. I want you to create an energy bar chart based upon the moment that it leaves your hand. So don't include the hand pushing the ball, just the speed that it's moving away from your hand up until the point where the ball gets to its highest point or its turnaround point. Hit pause, think about this, solve it, and then unpause to be able to see the solution. All right, so here's the solution. So right after it leaves your hand, we're going to look at just the earth and ball system. And so right after it leaves the hand, it's moving. All right. And it's moving at its maximum speed because, as you know, as something goes up in a gravitational field, it will slow down because acceleration due to Earth's gravity is downward. And so once you get to the turnaround point, the velocity in the vertical direction is zero and it's straight up and down. So the velocity, total velocity is zero. But all that kinetic energy is transferred to gravitational potential energy. And then it'll fall toward the Earth. All right, let's try one more. So now let's consider a spring-loaded dart gun. And so let's look at when the dart is against the spring inside the dart gun. That's your starting position. And then let's think about how fast that dart is going when it is leaving the dart gun and no longer touching the spring. So once again, hit pause, come up with an answer, and unpause when you're ready to see it. All right, so now what we have is elastic potential energy. So it's up, compressed against the spring. So that spring is squished, storing lots of energy. And then you release that energy and it becomes motion. And once it's done touching the spring, it's nothing but kinetic energy. So keep practicing and you'll do better.